This is the screencast for section 10.1, example 2, slope and concavity. So now here's where we dive into the derivative part of this. Well, we already know the first derivative of a parametric function back from section 3.6 is, the dy dx is going to be the derivative of y with respect to t divided by the derivative of x with respect to t, and that's because the dt's would kind of simplify out if you multiplied by the reciprocal of the denominator here. Now the second derivative gets a little bit more complicated. It's not just the second derivative of y over the second derivative of x. So first, the second derivative of y with respect to x again. Remember, the first derivative is going to have t's in it, so you can't just take its derivative with respect to x. We're going to rewrite the second derivative as the derivative of dy dx, which is the derivative of what we just said, dy dt over dx dt. Well, now in the numerator here, I'm going to take this derivative and I'm just going to take it of dy dt. So the derivative with respect to x of dy dt, and in the denominator I just have dx dt again, which then can be rearranged to be d dt, so the derivative with respect to t of that first derivative. So, and then of course still over dx dt. So you have the derivative with respect to t of the first derivative over dx dt. Now we're going to look at this in part C here, so hang on a second. Let's go through parts A and B. Example 2, analyzing a parametric curve. Consider the curve defined parametrically by x equals t squared minus 5 and y equals 2 sine of t for t between 0 and pi. Sketch a graph of the curve in the viewing window -7 to 7, -4 to 4, indicate the direction in which it is traced. Well, the book had a nice beautiful picture for me, so I just copied that down here. Then find the highest point on the curve, justify your answer. Well, highest is a y value. So I want to find the highest, the maximum y value, which means I'm going to take the derivative of y with respect to t, which is 2 cosine of t, so the derivative of 2 sine t is 2 cosine t, and I'm going to find its maximum. So the highest point on the curve has a y value of 2 because cosine's maximum y value is 1. So now I need to find out what t value that belongs to. So if I set my y value equal to 2, I can solve for t, plug that pi over 2 into my x parameter, and now I can see that x is pi over 2 squared minus 5. So now I have this point, pi over 2 squared minus 5, comma 2. Again, we found the maximum y value, so we took the derivative of y with respect to t. Found the maximum y value has to be 2. Found the t value it belonged to, plugged that t value into the x parameter to get what x would be at that same t. Now part C. Find all points of inflection on the curve, justify your answer. So points of inflection are going to be found in the second derivative. So that means I need to find the second derivative of y with respect to x. Now we said that that's going to be the derivative of, with respect to t, of the first derivative, then over dx dt. So the derivative of the first derivative is going to be the derivative of 2 cosine of t over 2t. So dy dt over dx dt. See, the derivative of 2 sine of t is 2 cosine of t. The derivative of t squared minus 5 is 2t. That's all going to be over then another 2t, because dx dt. Now I'm going to take the derivative of the numerator here, which is the derivative with respect to t of dy dx. But these two 2's can cancel out, so I'm just going to work with cosine of t over t. So now the derivative is going to involve the quotient rule. I have the denominator, which is now just t, times the derivative of the numerator, which will be negative sine of t, minus the derivative of the denominator, which will just be 1, times the numerator. And that's all over the denominator squared, so t squared. Remember, we've canceled out the two 2's. Then that was just the derivative of the numerator. I need to put that all over 2t, the dx dt that's supposed to be in the denominator of the entire expression. Now to simplify a little bit, let's see, in the numerator, well, let's factor out a negative sign first, get that out of the way. So now my whole numerator is positive, t sine of t plus cosine of t. And then if I took t squared and multiplied by 1 over 2t, the reciprocal of the denominator, I would get 2t cubed. Then using my calculator, I can see that this graph, the graph of this second derivative, is going to cross the x-axis at 2.798, which involves an inflection point. But that's at t equals 2.798. So I need to plug t into the x parameter and t into the y parameter to find out exactly what point that occurs at, and that's going to be 2.831, comma 0.673. Now try problem number 19. Says that x equals 2 sine of t and y equals cosine of t, and we want that for t is between 0 and pi. And we want to find the rightmost point. The rightmost point. Okay. A. Sketch the curve over the given t interval, indicating the direction in which it is traced. So on my calculator, I put in my x parameter and y parameter, found the window, x min 0, x max pi, and then found a good y min and y max, and then here is my curve, and it graphed, I guess, clockwise. So I'm looking for that rightmost point, and yeah, it looks like 2, 0. Okay, fine. So that's what part B asks. Identify the requested point. So now, at first when I did this problem, I went through all the actual calculus work, but then part C, look at this. Justify that you have found the requested point by analyzing an appropriate derivative. So B is only asking you to just see what it looks like in a very vague, poorly worded way. So it looks like 2, 0. Now don't you ever say that on a math test. It just looks like 2, 0, Miss Larson. No, no, no. Or AP grader. No, no, no. Part C. Now let's justify that. Let's make sure that 2, 0 is in fact the rightmost point. Well, the rightmost point is going to be a maximum of x. So we're going to take the derivative of the x parameter and use what we learned back in chapter 4 to find a maximum. 2 cosine of t is going to be 0, so the critical value is t is pi over 2. Now we only want that to happen between 0 and pi. Those are our t parameters, and here's our pi over 2, our critical value. We're going to test dx dt. So I get positive values between 0 and pi over 2, and then negative values between pi over 2 and pi, which means there is in fact a maximum at t equals pi over 2. So I need to plug in pi over 2 to the x parameter and then into the y parameter to find out exactly what point that occurs at, which is therefore 2, 0. So we did justify what it looked like from part B.